Hi everyone, my name is Willem Glerum. I'm a software engineer at Lunatech. I mainly work with Scala and Play framework in the past, and nowadays work building Java applications with Quarkus. Today we're going to talk about reactive Quarkus and going to explore a bit what is reactive programming, why you want to do it, and then of course show some code as well. Like I mentioned, I was mainly working with Scala and Play, and there are a lot of things are async. And I was a bit surprised that in Java and Quarkus, most of it was imperative and writing code. But nowadays, that changed a bit. Now they release quite some new reactive frameworks or libraries next to Quarkus. So we're going to explore in this talk how we can leverage and use that. So a bit more about Quarkus. Quarkus, for people that don't know, a web framework built on top of proven technologies. For example, think the JAX REST spec with RESTEasy, Hibernate, etc., and all building on microprofile and Jakarta EE specs. And then this talk will mainly be focusing on the reactive components. The program of today, why would you want to do reactive programming? What's the difference between blocking and non-blocking? I'll explain a bit Mutiny, that's a reactive programming toolkit. Next, we'll dive into RESTEasy reactive, the new Hibernate reactive, and also see how we can connect to external services in a reactive way with REST client reactive. And in the end, if we have some time left, we'll also look into publishing messages onto Kafka with reactive messaging. Nowadays, systems a lot of times built for resilience, and they're mainly based on top of the reactive manifesto. You probably heard that already this conference about reactive systems, or maybe tomorrow in some other talks. So I won't dive into deep into reactive manifesto, but I'll go over briefly. Nowadays, systems are made more flexible and loosely coupled and scalable, and that also makes them easier to develop and ready for change as well. And in the end, your main goal is that they are significantly more tolerant for failures. So they are highly responsive, give users always some feedback, and don't come up with a failure. We got 4 pillars here. On the bottom, we have the message driven. Everything in a reactive system should be message driven. Everything interacts with messages, so even if it's a failure, it will be a message, for example. Then we come to the elasticity. They adapt themselves to the fluctuating load depending on how many users you have or how many requests. And they also have to be resilient. They have to handle failures gracefully, like I mentioned before. And in the end, that all contributes to the top pillar being responsive, to always respond in a timely fashion to the user. And that's in short the goal. With the new reactive libraries in Quarkus, it makes it a lot easier to build such systems with those guarantees as well. If we talk about async, we always talk about I/O, input and output, and it's almost everywhere. For example, imagining calling some remote service, and that remote service doesn't have to be in the outside world. It could also be a service from another team or another application that you call. There you always have to wait for a response back. You want to interact with some database or some data store. You may prepare some queries, send it a query, and then if you will wait till the database comes back with the results. And at other places, you sometimes just want to send a message to a broker. And there are all cases of I/O where you either get something or output something. Um, People always ask me like, why would you do something non-blocking? Is that not way too complicated or why too much overhead? So that's why the question is to block or not to block. When do you want to do this and when don't you want to do this? And there are quite some advantages of writing blocking code. You can do imperative programming, which we're all used to, and it's really easy to write and see and explain to someone else as well, because everything executes sequentially. You can read step by step what's happening in the code and, well, reason about it. So that makes it really easy to write and read your code. It has some drawbacks, of course. It will contribute to a higher memory usage, and you have a limited amount of threads as well available to execute work. So if you run out of CPU, yeah, you can't do more threads, you can't do any more work. That's a bit the problem here, because if you want to serve more users, then you're gonna need some more threads. So you're gonna need another machine or another VM or another container running somewhere. For non-blocking, on the other hand, if you write some async code, you can handle multiple requests on the same thread. In the next slides, we'll see how that actually works. And the biggest advantage here is that you don't need all those context switches. For example, imagine that if you run something on a thread, you have to wait till something gets back. Then you have to dump it into memory, maybe switch to another thread. And that's all very expensive. In the non-blocking way, you try to handle those requests on the same thread. And that will contribute to a higher throughput, a lower latency, and lower memory usage as well, if you're lucky. And it's especially powerful if you run on the cloud. Imagine, for example, running on a big Kubernetes cluster. If your workloads go up, so you impact your applications. You don't want your application to cause other apps to go down as well. For example, they consume all the memory or the CPU, and you have the concept of noisy neighbors, which then impact the other apps running on that machine as well. And that's of course not what you want. You want to have more traffic flowing through your clusters. If we talk about worker threads, it's pretty common, at least in the past, it was pretty common to have one thread per CPU. Well, nowadays we have multi-threading, so we can have a bit more, or we can have a thread pool where you have multiple threads that you can use in your application. And if you run out of threads, you can't do any more requests in parallel. If you can see in this picture, if one comes in, it blocks the thread and does some work, and then nothing else can be done on that thread anymore. So if another request comes in during that time, it has to be spawned on a different worker thread. You can't handle that on the same thread anymore because you're blocking, because maybe the request 1 is calling the database and request 2 is calling some external service behind the scenes. And in that way, they can't be running on the same thread because they're both doing some blocking I/O, and they're both stuck waiting. So if now a third request comes in, you actually can't help the user with that request because you don't have any space left to execute the request. That was the blocking example. Now we go to the non-blocking example, which you are all here for. If you see in this picture, we squash them all together. So we see that we start with request 1, and then we schedule some I/O. So go to the database, and if you come back, then I'll gonna execute some other function. But in the meantime, I can do some other work. So for example, when that database query is running, you can actually have another request coming in. So request 2, you do some work as well, and then you decide to schedule some I/O. For example, when you were calling your remote service. And in the meantime, when you were calling this remote service, you dispatch that one. You actually got the result back from the database, and you got some time again because you have nothing to do because you just scheduled that I/O for the request 2. You can continue with the request 1. So have some callback there, transforming the database result back into some HTTP response again. Then you finished with request 1. You're still waiting for request 2 to be finished, but you actually don't really care about that. And in the meantime, we got the third request coming in. And if you saw in the previous picture, request 3, there was no room for it. And in this case, we have some room, even on the same thread, in the meantime, to execute request 3. And this goes on and on and on. And as you can see, with this way, you can pack a lot more requests on a smaller amount of threads. That's what we try to do here with writing non-blocking code. Now you're probably wondering, like, how would we integrate all those concepts together. So how could I write some blocking code and some non-blocking code together? That can be done with doing some context switches. So in the middle, you have some IO threads doing some work and dispatching that as well, and dispatching that to some event handlers. Maybe they need to do something else, and they uh, put the thing on the event queue, and they pull the event queue. Is something finished again? And then they can start doing some work again and dispatch it again to some other event handler. Well, if that dispatch to an event handler doesn't work, maybe you have to do some really expensive calculations that are CPU bound, then you would need to switch to a worker thread, because that IO thread can only do lightweight tasks and shouldn't be doing blocking operations itself. If you try to do that in Quarkus, you will also get some exceptions and warning telling you not to do this. So when the IO thread decides, like, well, I'm going to dispatch this to a worker thread, then I do a context switch and let the worker pool thread pool handle the event. And then it might come back again to the IO thread to handle back to the user. That's in short the differences between imperative and reactive programming, and a bit of the reasoning why we want reactive programming. The main reasoning being that we want to handle more requests with the same amount of CPU or the same amount of machines. Next, we want to have some toolkit as well to enable ourselves to be able to do reactive programming. And in Quarkus, we have multiple options for that. We can use the small array Mutiny library, especially developed for Quarkus as well. And that has a uni and a multi concept, which we'll explain later a bit. Then, of course, we can use the standard completion stage from the Java library with the completable futures. Or we can use the reactive streams publishers with RX Java or Akka streams, for example. And we can all integrate that together in the Quarkus application if we want. But in this talk, we'll mainly be focusing on Mutiny because that's made especially for Quarkus. So Mutiny is a reactive programming library. You don't have to use it for Quarkus. You can also just use it standalone in your software and use it there as well. It has two concepts. A uni, which emits a single event, and that single event can be an item or a failure. And this looks a bit like the completable future that we saw before here as well from the Java library. Then we have a multi, and a multi could emit multiple events over time. And it can be 0 to an infinite amount of events coming in over time as well. And that's a bit similar to the same concepts as the mono and flux, as you could see, for example, in Spring Webflux or Reactor as well. So they're pretty similar there. Now you're wondering, like, how would I use this uni, or what do I do with this multi? If you here we have some example code. When we start with the multi, we can create a multi from a bunch of items. In this case, 3 characters, A, B, and C. Normally, instead of getting here a static list here, those could be coming, for example, from a Kafka topic or a remote service asynchronously. So they could come in step by step. But for this example, we keep it simple. We just have 3 simple elements in the list. As soon as we have an item, we say on item, and then we transform it. And when we get that item, we transform it to an uppercase. People that are used to more functional style could also use .map in one go, and then you don't have to call on item and .transform, but you can call map or flat map and combine those two as well. Next, we subscribe to that multi, because now up till now we only just created the multi, and as long as we don't subscribe, nothing is going to happen. So we say we subscribe, and when we get one, we print it and we say we got one, And if we had a failure in between, well, in this case, we don't have any failures, but we could have a failure in our stream processing, of course. And then we would print out with a failure. Well, this is a really minimal example. In the real world, you would chain those pipelines and handle those failures, maybe do some other action when you have a failure. Next, we have the more simpler form, that's a uni. We also can create a uni from a dummy item, and in this case, it's just a character as well. We execute the same strategy, and you see this is just executed once if there was an item, and otherwise it would fail the uni as well. So that's in short the concepts of reactive programming and how you can use, for example, mutiny inside your application to deal with streaming data or with data that eventually arrives and comes from some external service. So how do we all use this? Because now it was pretty theoretical and we haven't seen much code yet. So we're going to see how we can actually do this and how we can implement this. We're going to build a new Quarkus project, and there we have a code generator. Then with the code generator, we can select a bunch of extensions, and with those extensions, we can build our application. Well, in our case, we want to have the reactive version of all the extensions. For example, normally you would use RESTEasy, the classic version with JSONB or Jackson. Use Hibernate as an ORM, for example. And then you need some JWC drivers as well to connect to either your Postgres database or some other database. But in our case, we want the reactive version. So we're going to go for RESTEasy reactive. And then we want to include some JSON serializers. So we're going to go with Jackson, the most popular one. We'll choose the newly created Hibernate reactive framework for our ORM needs. And then we'll choose the special Panache version. And that gives us some easy ways to query the data just out of the box without us having to write all the boilerplate ourselves. Next, we'll include the reactive Postgres drivers from Vertex. So they're not actually from the Quarkus project, but they're from the Vertex projects. They publish some reactive drivers. And you don't only have them for Postgres, you also have them for MySQL, Microsoft SQL Server, etc., etc. Next, we also want to be able to connect to some remote services, so we use REST Client Reactive. And for our Kafka messaging, we'll use the small array reactive messaging extension. Now, while we all gather this together, I can actually show you. This is live on the website. We can filter for some reactive libraries, and as you see, already selected some. But there's way more out there for you to explore regarding reactive libraries that you can use inside your Quarkus application. Now, once we all were happy with the selection, we can generate our application and download the application. And then open up the project. I already downloaded this before the presentation, so we can start right away. This, for people used to JuxRS and RESTEasy, this looks probably pretty familiar. You get some path endpoints, defining the endpoints of your application. You get for this controller, and then for a simple method, you have that it's a HTTP GET, and it produces some plain text, and in this case, a simple string. This is just coming directly from the code start. So I didn't even have to write that myself. Now we can also run the application, simple Maven Quarkus dev. And when it starts up, it's going to start my application. And it provides me some goodies as well. The first thing that's nice, now the Hibernate ORM is still disabled because I didn't define any entities yet. That's fine. Hibernate is the other one is also disabled. But the cool thing here is the dev services. Because I defined a Postgres database driver in my POM, it automatically spawns a Postgres database leveraging test containers and Docker in the background. So without me even having to do anything, it just spins that up in the background, and it does the same. If we would enable Kafka, for example, then we would get the same experience. Then we'll just boot a Kafka Docker container in the background and connect to it. When you shut it down, it will clean it up. Well, now that it's running, we can actually open it. And this is represented with our new page, and we can try out one of our endpoints, and we see that's actually working. What I like a lot about this Quarkus as well is the dev UI. It gives some nice experience for developers while you're in dev mode to see what's going on. So for all the extensions that we just enabled, we see some configuration options, some extra goodies. Can go directly to the documentation from here. So it makes it really nice and easy to work. For example, a feature that you can have is like you want to reset your database in between. Then it's a simple action here, and it drops your database and cleans it up for you. For example, you could inspect your Hibernate entities, or I can simply open up the Swagger UI of my application, and I see the endpoints that were there. Well, these are just the default endpoints provided to us from the code sample. So that's what you get. Next to that, where is it? We also have in local dev mode, if I make a code change, it will automatically reload. So in this case, if I say something else, so Devoxx, I just save the file and then reload my page. And then it says hello Devoxx. So that's pretty nice. That just works out the box. Next to that, we also have continuous testing. So you can see that the tests are paused now, but I can enable the test as well. So they continuously run in the background, running my tests. And if they need a Docker container for test containers, they will use a test containers as well to spin it up. And you can already see that my test is failing now because I actually changed the code. So, well, we're going to revert my changes. And then it loads again. And now the tests all pass again. So that's a very nice feature working with your project. You get really fast feedback. You can try it out in your browser or making some requests, and the test run again in the background as well. So if you make a test fail, we'll rerun that fail test again, and you get some quick feedback as a developer. And that's what I really liked working with the Quarkus framework. So that's a brief overview of what Quarkus provides us. So we have Quarkus dev mode with the hot reloading. When you make a code change, you get to see the changes. The continuous testing, you get the quick feedback. We have the dev UI to, as a developer, quickly change some settings or work with some extensions that you enabled. And we have the automatic dev service as well for dev mode and testing as well. And in our case, that's Postgres and Kafka being started automatically for you in the background. Now, we saw a small overview of a Quarkus application. Now we actually want to use the RESTEasy reactive version as well. So that's just another JAX-REST implementation built on top of Vertex. That's also what Quarkus is using under the hood, and has really tight integration with Quarkus. And the nice thing is as well, it has a performance benefit for both blocking and non-blocking endpoints. So even if you're still writing blocking code, you still get some benefits, you get some performance benefits, and it's a bit easier to work with as well in some cases. And that might become the default in one of the next releases as well in the near future. In the meantime, I prepared some other project where we can see the differences. So here we have our normal RESTEasy endpoint again, which is blocking. And then we have the reactive version of that same endpoint. You can have a look at the type signatures where we can now actually see this uni. So we create a uni from, again, a simple item, and we don't define any failure cases, and we provide it to this endpoint. Even if I'm defining a uni, I can still make the endpoint blocking by just adding a blocking annotation, and then it will still be executed on a worker thread and not on the event loop. The nice thing about RESTEasy Reactive is that we can define some exception mappers for a certain controller. So for this class, I can define an exception mapper that just handles the failures of this controller. Normally in RESTEasy, that will be globally for your entire application most of the times. In this case, it only works for this endpoint, for this set of endpoints. And that's I find it quite nice. If you have some special needs, it makes really flexible and easy to define such exception mappers. And so here, normally you would say return a uni, but we deliberately throw an exception, and then it should blow up. Now we can try running this application. And you can see that it's starting some containers for me in the background. This time also some dev services for Kafka, inserting some data in my database, some dummy data. And now the application started up. Now we can actually try this as well. So we now enable the Swagger UI so we can easily make some requests and inspect our application. And we can try it out. So this just simply returns the hello RESTEasy, and then we also have some of the other endpoints, for example, the reactive endpoint, which simply still is working. There's one major difference. If we enabled HTTP access logging, and you can see here that the hello request is being executed on an executor thread, and as we have a look above in the code, that's the case as well, because it's just a blocking call. So it's being executed on an executor thread. However, this reactive greeting is being executed on the event loop, because we now have the reactive version of this one. So that's how you can see as well as a developer, am I making stuff reactive, yes or no? You can see on which thread it's being executed, so you have a pointer as what's going on. And if we then try one of the other ones, so the blocking one, is gonna call a blocking request, and the exception is gonna throw us an exception as well with a nice error message.